to our From Chaos to Control Introduction to Systems Engineering webinar. So I'm joined today by Mark Williamson, who's our founder and managing director and course trainer. My name's Sarah Thomas. I'm helping facilitate the session today. I need to let you know that it's going to be recorded and transcribed. If there are any worries or concerns over that, please just raise your hand now and let me know in the chat. I have set your microphones to be muted for the moment, but I do believe that you'll be able to unmute at the end of the session to do a Q&A. And if not, we can pop any questions throughout the session, please pop them in the chat box as well. Today, the purpose of the session is to have a short taster session from our Introduction to Systems Engineering with Requirements writing course. There is going to be a little bit of information about what our course contains, but today Mark will certainly be giving some technical value in terms of all things in systems engineering. So I will hand the mic over to Mark, and thank you for your time today and joining.
Thanks, Sarah. I'll get straight into it. Hopefully you can all see my screen. See my screen, Sarah?
Yeah, we're seeing it.
Yeah, okay, cool. So yeah, welcome, as Sarah said, the first of our series of webinars on our Control-Alt Engineering series. And this one really about introduction to system engineering. So how can you start from chaos and start building in some control? A little bit about me. As Mark Williamson, I'm a member of Nkosi, and I'm an Nkosi CSEP and have been since 2013, going back a bit now. My background is I was ex-Royal Air Force, avionics, and ultimately a software engineer, and recently founded Optimize Engineering to support system engineering and tool support system engineering. So my main course delivery really is around this intro to SC that we're going to have a little bit of a taste of this morning, focusing a lot around requirements writing, because if you can't get requirements right, then your project's almost toast before you start. We also have an Nkosi System Engineering Certification Prep course. That's 4 days, which we'll deal with in the next webinar in a few weeks' time. And systems thinking, system of systems that we deliver an enterprise architecture. So that's really about me. Some of you may know me from history. So the agenda for this little sort of section is here. Really, what is system engineering? Yeah, people sort of bandy that term around quite a lot. What is system engineering? So we'll have a look at some of the definitions and what does that mean. You'd be surprised how many people don't actually recognize what the term system engineering means or what the domain means. And then we'll look at some of the key principles and look at some of the processes around system engineering, really aligned to the ISO 15288 standard, which is the basis for system engineering processes. Then we're going to have a look at the life cycle, the concept of life cycle. How do we manage the life cycle and the different life cycle aspects? And then a little bit, we'll finish off with a little taster on requirements fundamentals, how to write correct requirements, what correct requirements represent. And then, as Sarah said, we'll have a question and answer session at the end. Feel free to put any questions in the chat as we go along, and we'll try and pick those up as we go through. So, system engineering. It's really a cross-domain environment, whether it's nuclear, whether it's transport, whether it's aerospace, whether it's defense, whether it's a whole domain. All of these, anywhere you're building a complex system requires system engineering. So to manage the complexities of that and drill down into the engineering aspects. But it really doesn't matter what you're building. All the processes are exactly the same. All exactly the same. So what is system engineering? An interdisciplinary approach. And that's a really quite an important term. We've got safety engineers, we've got chemical engineers, we've got mechanical engineers, we've got center of mass engineers, lots of different technical specialities that have to work together in an interdisciplinary way to actually enable the realization, and this is the American speak of, manufacturing a successful system. So ISO 15288 I mentioned earlier. So this is the system engineering standard. and it really defines system engineering as a formal mechanism for development of a product. So we're going to build something that's going to be a product, and it really derives these two terms, supplier and acquirer. So if you're delivering something, you're a supplier. If you're acquiring something, if you're purchasing something, you're an acquirer. And quite often as a system engineering organization, you may be doing both of those in some sort of mechanism. So yeah, so all in all, development of a product or a system in a multidisciplinary environment with controls and processes. And that's what we're going to talk about quite briefly this morning. What are the controls we use to progress through the system engineering lifecycle? And how do we ensure that we tick all the boxes in the engineering lifecycle by actually using all the appropriate processes as defined within the ISO 15288. So we want to build something that meets the customer's needs, and ultimately from a quality perspective, that product has to be fit for purpose and meet the customer's needs. The other element of this is taking a holistic approach. We need to be thinking about the design and application of the whole system rather than individual parts, so that we might think of system elements composing of a system, and maybe those systems forming part of a system of systems as well. So really thinking about the bigger picture, how can we address that? So this is quite I wouldn't say a slightly busy slide, but these are the technical processes which I was referring to earlier. And this is the processes as per the new handbook version 5, the INCOSE handbook version 5, which aligns the ISO 15288 2023. So we have a whole lot of processes here, and those processes fall into certain pillars or for organization purposes. So I mentioned about supplier and acquirer a few minutes ago. Well, the agreement processes handle the acquisition and supply. So anything regarding to do with acquisitions, so maybe issuing invitations to tender or requests for proposals, or defining the statement of work, for example. And then on the supply side, how do we respond to that in terms of supplying a product and then establishing a contract and establishing an agreement? So you may well say, well, what's that got to do with system engineering? Well, we can't actually build and produce and sell something unless there's some sort of an agreement mechanism for doing that. So yeah, acquisition and supply are the two agreement processes. We sometimes refer to them as, both sides of the same coin. So they come hand in hand. And then down the left-hand side of this, we've got lifecycle model management, or organization project enabling processes. So at an organizational level, at an enterprise level, we need to have some processes in places to provide an enabling function for system engineering. And we got lifecycle model management. I'm going to talk about lifecycle in a few minutes, but what does your organization need to have in place to be able to deliver a system engineering project? So you're going to have some sort of lifecycle models. That may be agile, maybe lean, maybe plan-driven, maybe evolutionary, but there'll be a certain number of lifecycle models prepared on the shelf, ready to be tailored and used on project. Infrastructure management. Well, obviously we can't deliver any system engineering functionality if we don't have the infrastructure. Infrastructure is bricks and mortars, capabilities, test labs, all the facilities that you need to be able to deliver engineering. Portfolio management is really about, and something not a lot of system engineers often get involved in. This is about having a portfolio of projects, probably more oriented towards the chief financial officer type role, but having a portfolio of projects that the organization can call off and deliver to return necessary value to the business effectively. Human resource management, it's not HR, it's not about leave applications and holiday and sick pay and all the rest of it. This is about having the right people with the right skills to be able to deliver against your projects. And then we go into quality management. You will note there is quality management and quality assurance. So quality management really is how your organization can then align to your subscribed quality standards, so ISO 9001, for example. So a lot of process around how can we ensure that we're building the right product and meeting the quality standards effectively. And last but not least on here is knowledge management. Yeah, so this is something which is very often overlooked. So having a repository of information and work instructions, guides, need to know, all of the good stuff that's generally in people's heads. And we need to retain that within the business. Should that specialist leave the business, decide to retire, even worse, go to a competitor, how do we manage that? How do we manage that within the business to retain that knowledge? So knowledge management, making sure you've got a sort of Wikipedia, like, or a wiki of data, instructions, how-tos, etc., within the business. So that's the organizational project enabling processes. And then we have technical management processes. These are the overarching, on the technical side, obviously the management processes. So project planning, start with project planning. If we're going to start a system engineering project, we need to do some planning. So project planning is the first process here. And that really, the primary output of that project planning process is something called a system engineering management plan, SEMP. So along with subsidiary things like work breakdown structures and etc. But project planning, and this is done not at a project management level as such, but at a project planning level at a system engineering perspective. So there may well be some connectivity here or touch points with a program manager or a project manager, but this is really focusing on the system engineering effort required and the processes that will be followed and tailoring of the system engineering processes for this particular project we're kicking off. Once that's up and running, then we have project assessment and control. So this is just maintaining a record or a monitoring of the system engineering project so that we can ensure that it's on track, any corrective action need to be having, any leading indicators, any measurements that need to be taken to assess and control the project. We're going to talk about life cycle and how we move through that life cycle in a few minutes, but decision management, we have to make some decisions at certain points in the life cycle. So system analysis may be called to give us some subjective data in order to make that decision. So, and this could be called any decision you need to make in the life cycle at a decision gate or stage gate. This is where this occurs. Risk management, of course, risk is always an element, risk management, and then ultimately configuration management. Sometimes what I call a necessary evil, configuration management. It is absolutely critical that your engineering artifacts are under configuration control, change management. It just sometimes gets in the way of getting the job done, but then we have to manage that. So we're going to generate a lot of information, a lot of data. All of these processes will be generating reports and records and outputs and specifications. So we need to handle and manage that somewhere. So information management is the process that manages that. And I touched on measurement earlier. Measurement, we need to take measurements all the way through our system engineering processes. Things like measures of effectiveness, measures of performance, technical performance measures, measurements on our process, trying to improve our processes. So this process deals with how we do that and how we manage those measurements. And then finally, quality assurance, as I mentioned earlier, building something that's fit for purpose, making sure that the product we make meets all the requirements and specifications. So that's the overarching stuff, the organization, project enabling, and the agreement processes and the technical management processes. What we're really on about here with system engineering, the technical processes, what we call the technical processes, and there's 14 of those. And actually, I quite like the way that the new and COSI version 5 handbook has positioned this almost like a V model. So starting from a lifecycle approach, from the concept definition, establishing the business needs, the business mission analysis, then deriving those down into stakeholder requirements, so the first formal representation of a requirement. You may call them user requirements, they may be called system stakeholder requirements. So different domains will call them something different, but effectively, in terms of the handbook and specification, it's stakeholder requirements. Once we have the stakeholder requirements derived and defined, then we go down and derive those into system requirements, so system level representation of those requirements. That may well come along with sort of architecture definition and flow that down into design. You will notice these little circles and arrows. These are quite innovative, I believe, and sort of represent the iterative nature of system engineering. It's very, very rare, if ever, that you would actually have a single set of stakeholder requirements that derive into system requirements all in one iteration. Tends to be an iterative approach, tends to be a little bit of iteration and also recursion, where we're actually working our way down through different system elements as well. So, the equal sign here just means a little bit of concurrency. So there will be activities that are happening at the same time, like verification and validation are concurrent activities, if you like. So once we've assigned the system, we then go into system realization. So we're going to verify, we're going to validate, we're going to implement individual system elements, but then we're going to integrate those different system elements into a system of interest. And then finally, we're going to hand that over, that prepared system, to the end user from a transition process, operate, maintain it, and then finally dispose of it. And that's an interesting point. We need to be thinking about disposal requirements right at the beginning of the process, rather than waiting till the end. So if you're looking to do the COSI certification exam, you need to understand all of these processes, all of their inputs and all of their outputs and all of the activities across the handbook. So the V model, hopefully you're all familiar with the V model. So starting off with the stakeholder requirements at the top left-hand of the V, working our way down to system requirements, perhaps architectural requirements, subsystem, and implementation. As we're working our way down the V, we will be doing inherent validation. Are we building the right product? So as long as the subsystem, the system requirements, architectural requirements satisfy the requirements on the level above, then you're going to be validating you're still building the right thing. And as we work our way up the right-hand side, we're doing various levels of verification at the integration level, system level, operational level, and are we building the product right? Again, in the intro, the 2-day intro to SC course, we cover verification and validation at an introductory level as well. So, questions in the chat? Is there? Yeah, Sarah?
Yeah, there is actually, yeah, a good question from Matt Mendel. What are some of the most common mistakes that organisations make when adopting SC? Don't know if you want to tackle that now. It might be quite prudent to the slides you've just gone through.
Yeah, I'll tackle that now. It's a really interesting point, Matt. So, as we've just seen, if I just go back actually to this slide here with the processes, there's a huge amount of process here. There's a lot of regulation and regulator compliance and stuff going on. So one of the most common mistakes is you just throw everything at it. You know, we do everything just in case. So, and that obviously provides a huge cost overhead and may well even end up delaying the project significantly. So there's an element here called tailoring. So the whole purpose of tailoring is that all of these processes should be modified or reviewed or considered and tailored for the specific complexity of that system. So the real thing here is we don't want to be doing everything all of the time just to be safe. We need to have a considered, careful approach. And then probably the second thing of that is per requirements management. We'll get to that in a little bit, but if we don't consider requirements correctly and consider the acceptance of those requirements from a client, then that can cause significant issues later on. So we may accept requirements which are not actually feasible, or we may end up with scope creep, where the requirements expand, and obviously the system gets even more complex and outside of the scope. So that's probably the two primary things are common mistakes or errors that might occur in adopting SE. So three life processes then. I've mentioned these processes. We have a life cycle. Every system has a life cycle. So the purpose of through life processes is what we're going to look at the characteristics, look at decision gates. Decision gates help us to migrate through the life cycle, through the stages of the life cycle, from perhaps the concept, the development, production, utilization, support, and retirement stage. So these are the default or the generic ISO 15288 life cycle stages. Your organization will certainly have its own life cycle model. Certainly in the defense community, they have a life cycle called CADMID, Concept Assessment, Demonstration, Manufacture, In Service and Disposal. And I'm sure you will have your own life cycle models, but you have to have a life cycle to have manage the journey of that project from concept right through to retirement. So all systems have a life cycle, and it starts with maybe not even requirements. It stands for the identification of a need. What is the need here? What is the opportunity for adding some value or filling a capability gap or something? So identification of need. That will then flow through in the development, so stakeholder and system requirements and implementation, flows through into production, utilization, and finally decommissioning and disposal. Going back to tailoring again, system engineer will tailor the life cycle, including those key decision gates. How am I going to progress through this life cycle? What are going to be the decision gates? What are the milestones specific to that project? Tailoring again. Again, depends on how complex the system is. It depends whether that system may be part of a system of systems. But each stage, concept, development, production, utilization, support, and retirement, they all have a distinct contribution to the life cycle and need to be considered when planning that system engineering management plan and thinking how you're going to implement that project. So it provides your organization a framework and gives you good connectivity and control of the project, and those technical processes, those 14 technical processes we just looked at. This is a really, really important point. So regardless of the life cycle, there are three aspects we need to consider: the business, budget, and technical. Have we got a business case? And do we still have a business case as we progress through the life cycle? We may have a business case, but have we got the money for it? Have we got the budget for it? And is this product now a technical feasible product that we're producing? So at every single decision gate, stage gate that we progress through, we should be considering these three life cycle aspects: business, budget, and technical. Those aspects will then provide a bracket or a container for actually developing the technical solution. We're going to have to develop that solution as an engineer in accordance with the budget that we've got, the technical feasibility, the technical aspects that are required, and obviously still meeting the business case. So always as we go through considering and developing the system in accordance with these three aspects: business, budget, and technical, and need to be considered all the way through the life cycle and given equal consideration at each decision gate review. So, life cycle aspects, really important, really key that we maintain that consistency through the life cycle as we develop it. This is just some generic life cycles for comparison. We've got the ISO 15288, this is the 2002, it hasn't changed across the top. And then we have a high-tech commercial manufacturer, which has split that life cycle into three periods: the study, implementation, and operations period, and then split that period into a number of phases as well. US Department of Energy as well, another example, just breaking down the life cycle approach from start to finish, the different stages and gates, and some example gates at the moment at the bottom there. Concept, development. You might be familiar with more like the stakeholder requirements review, or a preliminary design review, or a final design review, etc. So different approaches. We established that we have a life cycle, but we can approach that life cycle or navigate our way through that life cycle in different ways. So plan-driven methods are very regulatory, very atypical on how a system engineering or complex system engineering project would do. Incremental and iterative, lean and agile are examples of those. I'm going to look at some of these as we go through. We look at all of these in the actual 2-day course. So plan-driven, really the traditional way to do system engineering. If you've got multiple organization, if you've got large complex teams, then it's really necessary that we actually have a very document-centric, very regulated, systematic approach, applying on and adhering to all of those system engineering processes. Very specific attention to documentation, to traceability of requirements, which we'll come to a little later, and verification and validation. So very regulated, very document-centric, lots of checks and balances to, generally the traditional way of doing system engineering. Incremental and iterative, as opposed to that, really works and tends to be used where maybe the requirements are less formalized, perhaps unclear. Maybe the stakeholder doesn't even know what he wants. So we're just going to actually start off, provide some initial prototype, initial capability, and then we'll let actually deliveries through that incremental mechanism to provide the end product in the end. So it's quite useful. It's good. Rapid value and response. You're getting continual feedback, hopefully from your customer or from your client, but and also provides the capability to add technology updates as they come available, because we're not actually prescribing that system early on in developing it. So it may work in some less complex systems, and certainly will be more appropriate in systems that don't have very clear requirements established. So, yeah, I've pretty much covered all of that. Very flexible, very fast, very adaptable, and lots of feedback in that. Sort of got ahead of myself a little bit. And then evolutionary methods. So, could almost be aligned to agile in a way, but so then we have planned deliveries or planned and regular periodic basis every time we're releasing a new deployable version. So yeah, evolutionary approach. The example here is a sort of DevOps, so secure DevOps environment where we're planning, coding, testing, releasing, deploying, operating, monitoring, and feeding back into a new approach. So it's a nice approach, if perhaps in a more of a software environment, but easily can be applied to system engineering. Okay, any questions on that so far? Any hands up? No? Okay, so I'm just going to touch very briefly on requirements, because obviously requirements are the key driver for system engineering. If you don't, as I mentioned at the beginning, if you don't have good requirements, have requirements well specified early in the life cycle, then it really is a disaster waiting to happen on your project. So, good requirements. I have to say, if it's clear, concise, and correct, you're going to be halfway there. So we need clarity in a requirement. It needs to be precise. There need to be precise statements. And ultimately, the requirement should be written to provide some avoidance of ambiguity. We want things to be really simple, stupid, if you like. Generally required, provided in a textual format, and hopefully using some form of requirements management tool so you can build that visibility in. So requirements really important, not just for defining the systems, but obviously driving into architectural design, how we're going to do integration, how can we do verification. A requirement is not a requirement unless it is verifiable. That's the bottom line here. So if you can't verify a statement, you need to rewrite the requirement in a way that is verifiable. And as much as we want to have our requirements nice and simple and have multiple requirements so they're unambiguous and clear, concise, correct, and all of that good stuff, every requirement has to have a cost. So make sure that when you're defining your requirements, you don't have we're not gold plated. We don't have extra requirements we don't actually need or not derived from our stakeholder requirements. So yeah, make sure and the key thing here is do requirements early. If we can left shift in the life cycle as much as possible, then that really gives us an advantage in establishing the requirements and minimizing rework and cost. So requirements analysis, lots of elements here. So who is interested in requirements? Well, executives of your organization, managers, practitioners, and these particular roles will have a different responsibility, a different interest. So at executive level, we want to make sure that our requirements have regulatory and contractual compliance. Yeah, we don't want to get sued effectively. We want to make sure we're compliant with various standards. So we've got SPICE, which is an automotive standard, CMMI, and make sure we're delivering on time and on schedule. Middle managers, really more focused on the actually how are our requirements being managed? Have we got really good traceability requirements? Traceability across the V, outside to external standards, external regulations. Have we got role-based access? We don't necessarily want everyone having the same view of the requirements, and we want to be able to reuse requirements as much as possible. And this is something we do very often and talk about very often in with our IBM Doors Next deployments. How can we make maximum reuse of those requirements and create efficiencies in the lifecycle development? We want to have a good audit trail, and we need to manage scope and change. So who has changed that requirement when and what have they done? Really important. And that's quite difficult to do with general office products. At a practitioner level, yeah, I want to have something that's a scalable repository. How can I manage my requirements in a scalable way? I want to be able to handle complexity. I want to be able to derive and have some structure and organization to my requirements as we go forward. There are some common aspirations. Ultimately, we want to improve productivity. We really want to reduce rework because rework costs an awful lot. And the later you go in the life cycle, the more cost is built in. We want to make our customers happy and ultimately meet our business goals. So common requirements. So carrying out requirements analysis. First of all, we need to define the requirements. We need to capture the requirements. We need to elicit the requirements from our customer or client, and maybe it'll be from a invitation to tender. You may have some quite high level customer needs that we need to generate. So it is an iterative activity. We're going to take those requirements. We're going to establish the requirements. We're going to feed those back to our stakeholder. Is this what you mean? And clarify that. So it's an iterative process as always. Analyze requirements and make sure that if there's any, come back to those lifecycle aspects, the business, budget, and technical. Are we asking for something really expensive here, something really technical achievement? I think there's a question in there. Matthew, yeah, how would the requirements analysis definition process work in an evolutionary method? So again, evolutionary has got lots of checks and balances. So as a constant review, and generally you tend to have your stakeholder embedded within that team doing that evolutionary environment. So you still have to capture the requirements, you still have to define the requirements, and actually the iterative function becomes even more apparent in that evolutionary approach, where actually you're checking that the requirements are still valid, and you'll be able to have some direct feedback and correct those and update those in an evolutionary in a cyclic approach rather than the plan-driven approach, which is really quite it is iterative, but it's quite more document centering and removed. Has that answered your question, Matthew?
Yeah, thank you.
Okay. So yeah, so we're moving forward. we need to be able to define the system in measurable categories. This goes back to verification again. So I said earlier, if a requirement is not verifiable, it is not a requirement. So to make a requirement verifiable, you need to define it in certain sort of categories. So quantity or quality or coverage or timeliness or availability. So yeah, the central locking shall lock all doors within 300 milliseconds. The system shall be available for 99.9% of operating spec. Something that you can measure against. And even with the boundary, the voltage shall be within plus or minus 200 millivolts or something. So you can test for that. You can verify that, and that's a way of how we can make our requirements verifiable. Yeah. So ultimately, once we've done this requirement solicitation and we've done the requirements review, and we've iterated over the requirements and we've refined the requirements and we've done some internal and external reviews, then we will have ultimately a stakeholder requirement specification. So again, we are not defining what the system is at this point. We are defining what the system shall do. So these system specification will have performance requirements, will have functional requirements, what we want the system to be able to deliver. It'll also have non-functional requirements, and these are equally as important. We shouldn't just think, oh, they're not functional requirements, they don't care. The abilities, I call it, availability, reliability, maintainability, training capabilities, etc., and any other constraints we've got on our requirements. Ultimately, we'll have a baseline set of requirements which are complete. They cover all of the requirements of the system or all the capability of the system, required capabilities. They should be non-ambiguous, so because you can bet your bottom dollar if a requirement can be misinterpreted in any way, then it will be. And if you're passing that out to a supplier, maybe to develop a subsystem, they return this system 6 months later and say, there you go, that's what you asked for. It says, that's not what we asked for. Well, that's what it says on the tin. So we need to make sure that they're completely non-ambiguous. Ideally, recording the requirements database of some sort. There's a whole variety of requirements databases out there, from IBM Doors, DoorsNext, JAMA, Polarian, Dimensions RM. You may well have access or used some of these in the past. But it is important, regardless of which requirements tool you select, you use a requirements database. Once you get past developing anything more than the more basic system, then the complexity and the traceability requires a requirements database of some form. It should be accessible to all authorized parties, as we say, and then released as a system specification, maybe that's soft copy or a hard copy. Our requirements, characteristics of requirement statements themselves, the individual requirements. So when we're reviewing our requirements and when we're writing requirements, we need to be thinking about some of these characteristics. And these are all from the ISO 29148. So requirement is necessary. So as I mentioned earlier, every requirement has a cost. So we want to make sure that we've only got requirements which are strictly necessary within our project. So necessary. It should also be implementation independent. Right up until the design requirements, it should be implementation requirement, what the system shall provide, not how it's going to do it. So on the ambiguous we've talked about as well, it should be a complete statement. An individual statement should be complete without requiring any other explanation. Ultimately, absolutely should be singular. The system shall do X. The user shall be able to do Y. So individual statements, even if you have to have lots and lots of them, individual statements. And those statements need to be feasible. When going back to our business lifecycle aspects, budget, business case, budget, and technical, we need to ensure that the requirements we're writing are technically and financially feasible. So no point saying something that the vehicle shall accelerate from 0 to 200 miles an hour in 3 seconds, because it's just not going to be able to. Not feasible. They should be consistently written in a consistent standard as well, and a consistent structure. And bounded, if you bound your requirement with a particular a limit, or like I mentioned earlier, that then makes it verifiable. So, and ultimately, if you're in a highly regulated industry, perhaps in the nuclear industry or the automotive industry or energy, those requirements need to conform to external standards and regulations as well. So some of the characteristics of requirement statements. So ultimately, the full 2-day course that we scheduled throughout the year, I think we've got a slide coming up that's got all our planned dates on. We cover verification and validation as well. We also cover configuration and change management, the old concept of a change requests and change proposals and the configuration change board and all of the good stuff around configuration and change management, which is so critical to system engineering development. And we also have, this is really, really popular. We have a group workshop on the morning of the second day on requirements writing. So we go through the practicalities on the first afternoon on what is a good requirement and how you write a good requirement and the structure of a good requirement. And then we put it into practice the next day. We split into groups and we define a system of your choice. Write some stakeholder requirements, derive some system requirements, develop some verification criteria for the requirements you're writing. And yeah, generally very popular. Quite have to put my hands up and say, right, it's like lunchtime now, we really got to stop. So people really enjoy that and get some practical workshop expertise in writing requirements, supported by myself to review what you're actually doing as we go around. This is our public course dates at the moment. Next one is 12th to 13th of May. I think we've got some significant interest for that. Sarah will be monitoring that and planning it. 8th to 9th of September, 1st and 2nd December. We hold these courses on the Lincoln University campus here at Spark House. And we look forward to welcoming you on one of those courses coming up. As an aside, if your organisation has a quorum of people who may be interested in intro to SC training, and it's much more cost effective to do that on your site, then I'm quite happy to come to site, and then it's just one level of expenses to pay instead of one. Please connect with us on LinkedIn. Our website link is there, and or give us a call. Go back to the old days and give us a call. Very nice to speak to you this morning. And pretty good time. You've got 15 minutes for any questions from any delegates. Any other questions? No.
Kind of a specific question, but it just came up at work the other day. If you had a requirement or were thinking of requirements for maintainability, something like an MTBF of some value, that would require the product to kind of be used for a significant period of time to get that value generally. How do you deal with kind of requirements like that?
Oh, well, I mean, if you say maintainability.
Yeah, like if you wanted to say the MTBF of the product to be a certain value.
So are you involved in doing FMEAs, Matthew?
FEAs?
So FMEAs, so failure mode effects, critical analysis, or MCCAs. So that's generally the system engineering methodology for establishing the likelihood of something failing effectively. What's reliability, perhaps maintainability, but then one depends on the other largely. So if you've done FMEAs, then obviously you're doing a strategic assessment of all of the system elements and the components and what might cause that to fail, and then coming up with a mechanism for improving or reducing the likelihood of that happening. There's also some techniques around sort of Monte Carlo analysis and things like that that can actually do some assessment of likelihood of failure, and then feeding that into what you need to do to maintain that system to ensure it meets its service level agreements.
Okay.
Have you considered any of that, Matthew? Are you doing that already?
I was just saying it's something that was brought up discussion that made me think about it, but it's not anything on the cards at the moment. But yeah, just thought I'd ask.
Amit, question from Amit.
Hi, Mark. Thanks for the presentation. So just a quick question. I'm currently working in an area which doesn't utilize systems engineering, and I'm having to tailor processes which obviously suit them and suit their delivery. What should I prioritize when doing so, or what should be the top 3 things that I should do first? Because I know I can't implement all of it in one go.
Oh, well, I mean, the first thing is make sure you've got your requirements captured correctly and managed. Building traceability. So think about how the requirements satisfy each other, how they can be validated, how they can be verified, and how they can be conformed. So if you've got your requirements right, and then you've got your verification validation, you said in the V, then I mean that's probably the holy grail, if you like. There's all the rest of the stuff that we can add on to it, you know, and the bells and whistles. But if you've got your requirements, I mean, I can't stress enough how important requirements definition and management is. Yeah.
Okay.
So yeah, that's a key thing. Yeah.
Okay.
Thanks for the question, Amit. I think that's everybody now, isn't it? Have we lost somebody in the call, I think? Okay, Sarah, I think that's pretty much it. If there's no more questions.
Brilliant. Thank you, Mark, and thank you for all the contributions and for delegates' time this morning. I will arrange for the recording to be sent out and do a quick follow-up just to sort of recap on some of what has been spoken about today. And feel free to obviously share those recordings, etc., with your colleagues.
Yeah. And just one thing, we have got a part 2 of the CTL+ALT Engineering webinar series is in a few weeks' time, and it's looking at really the benefits and a little bit of info around INCOSE certification if you're considering a A-step or C-step certification with INCOSE to the V5 standard. So perhaps we'll see you there in a few weeks' time.
I'll include details of that as well.
Thanks so much. Cheers.
Okay, thank you.
Thank you.
All the best. Bye-bye. Bye.
Bye-bye.
Thanks all.